Good evening, students. In the previous video, I have explained to you what is meant by electric field and electric lines of force. So, electric field is defined as the space or area surrounding a given charge, inside which any other test charge will experience an electric force of repulsion or attraction. And if it is a point charge as well as a positive charge, the direction of the electric field will be radially outwards. Suppose if the given charge is a point charge and a negative charge, means the direction of the electric field will be radially inwards. Okay, how did we define the electric lines of force? These are the directions along which a test charge of +1 coulomb will tend to move in the electric field. Suppose if the given charge is a point charge and at a point P, which is a distant r from the given charge Q, we have derived the expression for the electric field E is equal to Q by 4 pi epsilon naught r square, and the direction is outwards. Okay, suppose if any other unit positive charge is placed along this electric field, means then the unit positive charge will tend to move along this straight line. So these lines only are called as the electric lines of force. Otherwise, we are going to call them as electric flux lines. Okay, my dear students, today's topic is electric flux. Let us now define what is electric flux first. Then we will try to understand. Okay, electric flux is denoted by the Greek symbol phi. It is defined as the total number of electric lines of force crossing through a given surface. As I told you that the flux lines are nothing but the electric field lines which are passing through a given surface. Now let us take this picture and understand. You see that here these parallel lines are directed along the positive x-axis. So these lines represent a uniform electric field denoted by the symbol E. Inside this electric field, I have placed a rectangular sheet whose total surface area is denoted by S. In the second picture, inside the same uniform electric field, the surface area S is placed parallel to the field. And in the third picture, neither perpendicular to the field nor parallel to the field, the area S is inclined at some angle theta with respect to the direction of the uniform electric field. Good. Now we want to define what is meant by electric flux. Now I want to compare it with a simple example. Okay. Imagine this is a cardboard sheet. This rectangular sheet of surface area S is a cardboard sheet, and all these lines of force you assume as arrows shot, okay, from a bow. And when powerfully shot arrows are coming towards the cardboard, means in the first picture, since the cardboard sheet is perpendicular to the direction of the arrows, all the arrows will pierce through the cardboard sheet with the maximum force. Okay, so that they will come out piercing through it. Now in the second picture, you tell me, suppose if the cardboard sheet is held in this position, means will a single arrow at least will pierce through the sheet? It will not pierce through the sheet because the sheet is held parallel. In this position, there is no arrow passing through the sheet. It is zero. Similarly, in the last picture, you see the sheet is held in the inclined oblique position. And here also I have shown as if all the four arrows are passing through the sheet. But will they all pierce and come out to the same force? Not at all. So in the first picture only, the arrows all will pass through the sheet and also come with the same force, with the greatest force. This is the simplest example I can give to understand electric flux. Now let us imagine that the uniform electric field is denoted by capital E, and the rectangular sheet of area S is held inside the electric field. Whenever an area is kept inside an electric field, the area is considered to be a vector quantity. What are vectors we have studied? These are the quantities which possess what magnitude as well as direction. Now what should be the magnitude of this rectangular sheet area? is denoted by S. S it's the magnitude of the area. If area is a vector quantity, means it will have a direction. So how to find the direction of this area vector? It's very simple. You draw a normal, you draw a perpendicular from the surface, and the unit vector along this perpendicular is denoted by n cap. So n cap is the unit vector passing perpendicular to the area of the given sheet, and this is the direction of the area vector. Okay. Now there are two vectors involved in this picture. One is electric field vector and the second one is area vector. The direction of the area vector is given by the unit vector n cap. Okay. Now let us redefine what is electric flux. So electric flux is defined as the total number of electric lines of force crossing through a given surface. Now first of all, here the total area is denoted as S. In this total area, I will consider a small area. You just look at this small area, all of you. This is the small area, rounded area is small area, and it is denoted by the symbol delta S. Delta S, which is a small portion of the entire area. So you look at this picture. In this area, only one line of force is crossing. Only one line is crossing. Is it not? In the entire area means now 4 lines are crossing as per this picture. So in this small area, the flux passing through that area also will be very small. So I am going to use the symbol delta phi. So delta phi is a very small electric flux passing through the small area delta S. Therefore, mathematically, the elementary flux, that is the elementary flux, means which is passing through the elementary area delta S. So the elementary flux passing through the elementary area, means a very small area, infinitesimally small area delta S is given by delta phi. This is denoted by the symbol delta phi, and mathematically it is defined as a dot product of the two vectors. So this is a E vector dot product delta S vector. So mathematically how we have defined electric flux? It is the dot product of the electric field vector and the elementary area vector. Since the area is elementary, through that small area only a small flux only must have passed through, and that small flux is denoted by the symbol what? Delta phi. So if it is A dot P means the dot product of two vectors is also what is the dot product of two vectors? It is a scalar and its magnitude. Okay, so this is equal to E into delta S into cos of theta. Is it not that? Okay. So delta phi is a dot product of two vectors, and hence this must be equal to a scalar quantity. Okay. Therefore, what should be the total flux passing through the entire area? Delta phi is only the very small flux passing through the very small area delta S. Therefore, what is the total flux due to the entire area? So therefore total flux through the entire area. So through the entire area means what the total area is? Yes. So that is given by flux. Flux is equal to summation of delta phi. The symbol is what? Sigma. Sigma delta phi means what? You have to divide the entire area into small elements. Through each element how much electric flux is passing, you add all the flux passing through all the elements. Then you will get the total flux passing through the entire area. That is the meaning of the word sigma. So this is equal to what? Sigma E ds. So sigma E dot delta S, and this is equal to sigma E into delta S into what? Cos theta. So this is equal to E cos theta into sigma delta S. So sigma delta S is equal to what? The total surface area S itself. Sigma of delta S means add all the small unit areas, you will get what? The total area. So here the sigma delta S is nothing but equal to the total surface area S itself. Therefore, the total flux phi is equal to what? E into S into cos of theta. So this is the expression for the electric flux. So total flux phi is equal to what I said? E into S into cos theta, where S is the total area. Okay. Now you look at the picture and tell me, in the first picture, the area is denoted by n cap. So what is the direction between the two vectors, namely the area vector and the electric field vector? Theta equal to, both are in the same direction. Therefore, what must be theta equal to? So in the first case, theta is equal to 0. Is it not? So theta is equal to what? 0 degree. And cos theta is equal to cos 0. Cos theta is equal to cos 0 is equal to 1. Therefore, the total flux is equal to what? E into S into 1. So this is equal to what? Flux, and this is the maximum value. This is the maximum value of the flux. Now in the second picture, you see here the area vector is pointing upward, that is perpendicular. So this is perpendicular to the electric field at all points. So this theta here in the second picture, what is theta? Must be equal to 90 degree, and cos theta is equal to what? Cos 90 is equal to what? 0. Is it not? Okay. That means, therefore, what is flux phi equal to? Phi equal to E into S into 0, and that is equal to 0. So this is a flux phi is equal to 0 in the second case. That is why no single line will pierce through the area. It is very clear from the picture itself. Now general expression, you can see that the third picture is theta is any value. So in the third picture, for theta, for any value of theta, the flux phi is equal to E into delta S or E into S into cos theta for the total area. Now, what is the unit? What is the unit for this flux? We will find out that the unit for flux, unit of flux is given by, see here, from the definition of flux is a dot product of which two quantities? That is electric field and area. Is it not? So this must be equal to what? Electric field is what? Newton per coulomb multiplied by meter square. This is the unit for area. Therefore, rearranging this, this also can be written as what? Newton meter square per coulomb. Newton meter square per coulomb. Newton meter square per coulomb is the unit of the electric flux, which is a scalar quantity. So I am repeating once again, electric flux is denoted by the symbol phi, and it is defined as the total number of electric lines of force crossing through a given surface inside an electric field. I hope you must have understood. Now we are going to study Gauss' law, which is based on the electric flux. Okay. Let us now explain Gauss' law. Gauss' law states that the total flux phi over a closed surface is equal to 1 by epsilon naught times the total charge enclosed by the surface. So Gauss' law relates two quantities, you must know. What are the two quantities related by Gauss' law is? One is the total flux which is passing perpendicular to the given surface, and the second one is the total charge enclosed by a closed surface. So in this picture, I have taken a positive charge plus Q. Since it is a positive charge, the direction of the electric field lines of force should be radially outward. So, with respect to the center, the electric field lines should be radially outward in all the directions. But I have shown only one such electric line of force. So, this is the direction of the electric field, and since the given charge is a point charge, the electric field shape must be a sphere. So I will assume an imaginary spherical surface surrounding the given charge. You imagine an LED bulb is kept inside a glass sphere. Will the light pass through each and every point on the surface of the sphere or not? In the same way, I imagine a charge is placed inside a spherical imaginary surface, Okay. Now, one such lines of force is passing perpendicular to the surface. So, what should be the direction of the area vector drawn at any point on the surface? I have told you the area is a vector, and area vector is having a direction given by the unit vector passing perpendicular to the surface area. Now, you imagine the entire sphere is having a surface area denoted by capital S. So, S is the total surface area of the sphere, and out of the entire surface, let us consider only a very small surface denoted by delta S. You can see here delta S, which is the shaded region. Okay, this is a small circular area on the total surface area. So, through this small area delta S, only a small flux delta phi must penetrate. So, I will take here delta phi. So, delta phi is the very small elementary flux passing through the elementary area delta S. Finally, what we have to do? We have to add the flux passing through each and every small elementary area throughout the entire sphere and find the total flux. So, I have considered delta phi is the very small elementary flux passing through the very small elementary area delta S. So, mathematically, this elementary flux delta phi must be equal to what? The dot product of what? So, E vector dot product delta S vector. So, this is equal to E into delta S into cos of theta. And this is equal to E into delta S into cos 0. So, cos 0, because here you see that this is the area vector. The area vector is perpendicular to the surface, and it is along the direction of the electric field. Therefore, here what theta? Theta must be equal to what? 0. Theta must be equal to 0. And hence cos 0 must be equal to 1. Therefore, this is equal to what? E into delta S. So, we have got an expression for the very small elementary flux passing through a very small elementary area delta S. Now, how to find the total flux passing through the entire surface area of the sphere? We have to do the summation, okay? Therefore, total flux, the total flux passing through the entire area is given by phi. Phi is equal to sigma delta phi. So, what is the meaning of sigma? I told you, each small area delta S we have to consider, and through each area how much flux is passing through we have to find out, and we have to add all these elementary flux to get the total flux. Okay, but you see that at each point on the sphere is at the same distance. Suppose if you take a point here or below this or left side or on the top, all are at what distance from the center is equal to the radius of the sphere. That is a small r. Small r is the radius of the imaginary sphere, which I have considered around the given charge. Now, at all points, the electric field will be the same. So, I can write this as what is sigma E delta S. So, this is equal to what is sigma E into delta S. That is equal to E into sigma delta S. This is another equation. So, the total flux is given by what? E into sigma delta S. What is E here? E is the magnitude of the electric field at any point on the entire sphere. All points on the entire sphere are at the same distance r from the given charge. Is it not? Because these are all symmetric points on the sphere. They will have the same electric field. So, I will write the expression for what? The magnitude of the electric field at any point on the surface of the sphere, and that is equal to what? 1 by 4 pi epsilon naught into Q divided by R square. This is the magnitude of the electric field at any point on the sphere, because all points on the sphere are at the same distance R. So, in the previous topic, we have derived an expression for the electric field at any point P at a distance R from the given charge Q. So, that must be equal to what? 1 by 4 pi epsilon naught into Q by R square. I am going to substitute the expression for electric field in the previous equation, that is flux phi. Therefore, what is phi is now equal to E into delta, that is sigma delta S, E into sigma delta S. So, this is equal to 1 by 4 pi epsilon naught into Q by R square. Q by R square into sigma delta S means what? You have to add the small elements of area delta S so that you will get the total surface area of the sphere. So sigma delta S must be equal to what? The total surface area of the sphere of radius R. So what is the mathematical formula to find the total surface area of the sphere? It is 4 pi R square. So I am writing what? The total surface area must be equal to what? That is 4 pi into R square. Okay, which are the terms getting cancelled? First 4 pi and 4 pi get cancelled, R square and R square is getting cancelled. What are the terms remaining is Q and epsilon naught only are remaining. Therefore, flux phi is equal to Q by epsilon naught, or flux phi is equal to 1 by epsilon naught times the total charge Q. So we have got the mathematical statement of Gauss law, which states that the total flux phi over a closed surface is equal to 1 by epsilon naught times the total charge enclosed by the surface. That is very important, my dear students. In this picture, one and only charge is given. That's what the magnitude is, plus Q coulomb. In the same picture, now say for example, I will take plus 4 coulomb, okay, then plus 2 coulomb and minus 5 coulomb, 3 charges. I have considered 3 charges, plus 4 coulomb, plus 2 coulomb and minus 5 coulomb. 3 charges are located at the center, means we have studied the algebraic sum of the charges. Okay. So what is the algebraic sum of these 3 charges? 4 plus 2 is 6. 6 minus 5 is equal to 1. So the net effect is what? Plus 5 plus that is a Q coulomb only, is it not? So similarly, this plus Q means it may not be a single charge always. It need not be a single charge always. It may be the algebraic sum of more than 2 or 3 charges also. So it is always to be remembered that small q is not a single charge, it is a net charge, the resultant charge located at the point. So once again I will repeat Gauss law. It states that the total flux phi over a closed surface is equal to 1 by epsilon naught times the total charge enclosed by the surface. So finally mathematically was phi is what? The total flux. Q is what? The total charge. Are they related? 1 by epsilon naught times? Okay. So epsilon naught already we have defined that it is the permittivity of free space. Now you tell me here flux phi is having a unit. So what must be the unit of flux, you tell me? This is equal to what? Electric field into area only, no? Electric field into area. So electric field into area means what it is? This is Newton per coulomb. This is Newton per coulomb and this is what? Meter square. So E is electric field. It is having a unit of what? Newton per coulomb, and area is having a unit of what? Meter square. So this is equal to Newton meter square per coulomb. Okay, have you all understood? Now the next topic is what? Applications of Gauss law we will be seeing later. Okay.